Hi, this is an example problem from Chapter 10 that has to do with elastic potential energy. Pause for a moment and read the question. All right, so we're going to use conservation of mechanical energy in this problem because there's no friction on the surface which the simple harmonic oscillator, the mass, is oscillating about. And so the only force that we need to consider is the spring force. And therefore, the spring force is a conservative force, and it has a potential energy, the elastic potential energy, defined for it, and so we can use conservation of mechanical energy to solve this. Now let's quickly go back and look. The mechanical energy we've defined as the sum of all the potential plus all the kinetic energy. Initially we just had gravitational potential energy and translational kinetic energy. We saw that you can add rotational kinetic energy. Now we're going to add elastic potential energy, the potential energy stored in a spring when it is stretched or compressed. In this problem, we have no rotation, so you can ignore the rotational kinetic energy, and the problem is not involving height. It's only horizontal, so we can ignore the gravitational potential energy. So in this problem, we can write that the total mechanical energy in this case, Emec, is just equal to the total kinetic energy, which is the ordinary translational kinetic energy, plus the total potential energy, which is the elastic potential energy, due to the spring. Now, as we saw, we have, for kinetic energy, we've got the good old formula 1/2 mv squared, and for potential energy, now the new equation, 1/2 K is the spring constant, X is the displacement from equilibrium squared. And of course, we're interested in the speed and the position displacement from equilibrium for these two quantities. So we have a nice little picture of here, and this is a good way to think about it. Draw a initial and final. So this is where we have our initial situation, where we are released from rest here. And later on, when we're at a position let's see. This is for part B. This will be our final position for part B. But for part A, let's look at how we do that. So for part A, I want to figure out what is the total mechanical energy. Well, it's conserved. That means at any instant, any point in the oscillation, the total mechanical energy has the same value. So we can pick a convenient point, right? Let's use the good old equation that we just wrote down. E mechanical is equal to 1/2 mv squared plus 1/2 kx squared. And I'm going to choose the initial position that we outlined here, right at the top, as the point that I want to evaluate and solve for the mechanical energy. And that's because if we look at it, the speed there is 0. So that whole term's gone. Now to figure out the position, here's your equilibrium position, x equals 0 here. This is what we call equilibrium. And the object here, initially, it's displaced from equilibrium by an amount 4.5 centimeters. And so we know what x initial is, right? So here's Emec initial, which again is Emec at any time. We can write it like this. This was 0. So let's go ahead and solve for that. We've got a 1/2, the spring constant's given, 545 newtons per meter, and the position, convert that to meters, that's going to be a 0.045 meters, and we square that, and we're going to get an answer here, and when we calculate, we get an answer of 0.552 joules. Now we know the unit of energy is joules. Over here we see that we have a Newton per meter times a meter squared, which gives us cancel one of the meters out on the top. We get a Newton times meter, and that of course is a joule, so we're good to go there. Let's look at part B. Part B, we're going to go ahead and determine the final translational speed of the object when at the final position when the displacement is x final 2.25 centimeters. So in this case, we're going to go ahead and look at this position here. And this is x final, and it's equal to 2.25 centimeters. And what's the speed right here? B final. We're going to try to figure that out. Now I can compare any 2 points, right? So I could say like the initial point, right? Emec initial, it's the same total value as Emec final, right? And I'm going to go ahead and plug in KE, PE for each of these. But for the initial, we already know what the total mechanical energy is. I'll just plug in the value that we just solved for here. And for the Emec final, I'm going to go ahead and plug in the kinetic energy at the final position, plus the spring elastic potential energy at the final position. And so there we have it. And we are, of course, trying to solve for V final. So we got to do a little bit of math here. Let's go ahead and rewrite this equation. So we're going to have mv final squared divided by 2. I'm going to subtract from both sides the term 1/2 kx final squared, and let's keep on going here. We're going to need to multiply both sides by 2 divided by m, and when we do that we will cancel out the m and the 2. Of course, that's why we did it. Left with v final squared is equal to, I've got a 2 over m multiplied by 0.552 joules minus kx final squared divided by 2. And finally, we just need to take the square root of both sides, right? So let me square root this here, square root this here, and we're going to get an answer here for v final. And we just need to plug in our numbers. So let me pause it for a second here. Well, I'll just keep going. 2 divided by m is 0.2 kilograms. And we've got a 0.552 joules minus, now we've got here K is equal to 545 newtons per meter. We've got X, which is 2.25 centimeters. That's going to be a 0.0225 meters. And we need to, of course, square that one. And finally, that whole thing is going to be divided by 2. And if we put that into our calculator, let's see what we get here. It comes out to about 2.03 meters per second. All right, we can check out and see if the units are right. Let's look at this term here. We've got a joule, and then we're going to divide it by a kilogram here, right? Then we got to square root the whole thing. What do we get? A joule, kilogram, meter squared per second squared, divided by a kilogram. Cancel our kilograms. We're left with the square root of meter squared divided by second squared. That gives us a meter per second. So we are good to go with our units. Everything looks all right.